Welcome to another module on the probability of weather type. This one talking about isothermal warm layer scenarios. What we're talking about here is the elevated warm layer. And in this situation, I'm just showing the yellow elevated warm layer that we all as meteorologists are aware of. And just a reminder that when the top-down approach is used within the probability of weather type, we use this curve to diagnose precipitation types from that maximum wet bulb temperature aloft. And so in this scenario, if your surface temperature is less than 32 degrees, basically we have an elevated warm layer, and it is a deep ice cloud process and no probability of ice grid exists. These curves are used to diagnose the precipitation type. So as we move on the spectrum from 1 to 4 degrees, we are basically taking a hydrometeor, moving through that warm layer and melting it to completely liquid by the time you get to 4 degrees. There's a second scenario if the surface temperature is greater than 32 degrees and there's warm layer aloft, as well as surface temperature being above 32 degrees, an isothermal layer above 0 Celsius is assumed in the probability of weather type. And in this scenario, things are a little bit different. Maximum wet bulb temperature aloft, if it's greater than or equal to 1, going to give you an all rain scenario. If it's between 0 and 1 and the temperature is right near 32, 33, it's too close to call for a precipitation type. And so we develop an equal probability of pellets, rain, and snow in that scenario. But we really want to concentrate on what happens with these curves for these elevated warm layers that may be isothermal. So recall back to the top-down methodology that the maximum warm layer or maximum wet bulb temperature is assessed because of this relationship. It's simplified and we just use that max TW aloft or max temperature aloft because of the relationship between the depth of the warm layer and the maximum temperature in the warm layer and the correlation coefficient of 0.8. Now that doesn't describe all warm layers, correct? This is just this relationship here describes some of them, right? The correlation coefficient isn't 1. So in this situation, it's mainly diagnoses well, the top-down approach will diagnose well these warm layers that have this triangular appearance. And likewise, it could be a cooler maximum wet bulb temperature here, and the depth is proportional to that cooling. So we have a nice, if you will, triangle approach here to that warm layer. But what happens in a scenario that's isothermal? This is where the top-down approach can fail you in its diagnosis of precipitation type. So here we have an isothermal layer that runs at about 2 to 3 Celsius for quite a bit of depth there. And so we're really losing out on what this triangle normally would look like in this environment. We're losing out on the assessment from the top-down approach. We're failing basically. And we fail the assumption that we make early on with this top-down approach that the depth is proportional to the max TW. So in reality, what you'll end up with is an observed precipitation type will be warmer than what the top-down approach would give you. So in this case, the top-down approach being in the 2 to 3 Celsius range, right here, would window with a high probability of sleet, so 100%. In this case, though, it's such a deep, warm layer that you're going to get full melting of that hydrometeor as it comes in as ice, full melting, and then freezing near the surface. So the chances of it falling as sleet are quite low, and your higher probability would be towards liquid. So in actuality, we have to migrate to a warmer precipitation type than what the probability of weather type would give us. So here's a sounding that was sent from St. Louis. As an example here, we have some ice that's being made, very similar to the sounding I just showed you, falls into this warm layer, and it's a very deep warm layer at 2 to 3 Celsius because the top-down approach uses the max wet bulb temperature aloft. It's going to be somewhere around 2 or 3 C and be an all sleet sounding. But really, these hydrometeors are melting to fully liquid drops by the time they reach the surface, and depending on the surface temperature, it's either going to be freezing rain or rain. So how does the forecaster account for this? The max temperature aloft in these scenarios is going to yield a colder precipitation type. For example, it's going to yield ice pellets instead of freezing rain. So the forecaster simply edits the max T aloft here to account for a warmer precipitation type. It's not always this isn't really the recommended way to do it in most cases, to use the probability of weather type where you're kind of reverse engineering. You're kind of thinking, okay, I really want freezing rain out of this scenario, so I'm going to build in the environmental variables. But in this case here, we have to edit the environmental variable max TW aloft grid to a warmer temperature to simply to get out of this sleet regime here in the 2 to 3C and get towards the liquid regime. So in this case, I would take my max TW aloft grid and edit it from 2 to 3 Celsius over into the above 4 Celsius range. And that way you'll get complete melting of the hydrometeor. So let's look at what this looks like very briefly in GFE. I've got a temperature grid of 31. My dew point and wet bulb are equal to 31. I just put in a pop grid of 100. And so here's my temperature, wet bulb temperature aloft. You can see 2 to 3 Celsius in this broad area that would mimic this sounding in this case. And then you also see the warm layer aloft down in the south is all over 4 degrees. And so we have a 31 degree surface temperature and very warm air to the south. And so what this is going to give me is it's going to go back and use those sleet curves and give me some sleet in this regime. So let's just keep moving through our top-down grids here. No prob ice present and no refreeze to sleet. So let's look at what the forecast looks like. I have no probability of rain. That makes sense. Probability of freezing rain is quite high, above 4 Celsius, because the curve, again, remember, is for above 4 Celsius aloft. So that's where you're seeing there's the max wet bulb temperature aloft. That's where you're seeing that freezing rain probability go to 100%, all warmer than 4 Celsius. And then to the north of that, in the 2.5 to 3 degree range, you notice you're having lower probabilities of freezing rain because you're just starting to pick up that curve of the freezing rain. And sleet, really high on this one. Okay, so in this scenario here, what you want to do is you'd want to warm this entire area through the middle portion of the forecast area here to 4 degrees, above 4 degrees Celsius to get sleet in this forecast. So that's how you migrate a forecast in these isothermal warm layer situations that are near freezing near the surface. Remember, these curves are kicked into action in the code when the surface temperature is less than or greater to 32. There's also the scenario where the temperature is greater than 32, so let's run through that one. That code is a little bit different. There we look at the max temperature aloft, and we assess if it's over 1 Celsius, it's going to be rain, because we figure then it's an isothermal layer above 1 Celsius all the way down, and that will have an all rain and liquid outcome. If it's around the 0 to 1 Celsius range, again, we have a pellet rain snow scenario. So let's go through that same gridded forecast here. We're going to alter it a little bit though. I got 33 temperature and dew point and wet bulb temperature, so I've got a warm boundary layer, the same pop, and the same max wet bulb aloft. So I haven't changed that at all. And so 0 to 1, just so you can see it, was up in this area here. I've got no prob ice or prob of refreeze sleet grid. And here are my outcomes. Rain all the way up to 0 Celsius aloft. I've got no freezing rain because temperatures are 33 and my wet bulb's 33. And my sleet grid there is right in that 0 to 1 degree temperature range that you see the sleet showing up. And there's the 1 degree aloft and 0 degrees. And just to highlight this a little bit better and turn these menus off. So you see the sleet now is in that 0 to 1 range because we don't know how the thermal profile will hug the 0 degree isotherm, and it's almost like a too close to call. So we make equal probabilities of rain, sleet, and finally we can go down to snow as well. And you can see the snow in that 0 to 1 range, but also to temperatures that are colder. So I hope this quick review of isothermal warm layers helps your understanding of how the probability of weather type works and how you can better, as a forecaster, edit your environmental grids to get the outcome that is needed when these types of failures in the probability of weather type occur.